a topic that is of my great interest. It's investigating what drives heat waves and the role of the ocean and atmosphere and their interaction on all time scales. I want to thank my collaborators here, Sankit Lee, Robert West, and Dongmin Kim from NOAA AOML and CMAS, as well as Louis Jia from GFDL Laboratory. So as Ray mentioned, I'll talk to you about heat waves and a specific event that occurs last year over the Western US. Last year, 2023, was a very special year for extreme temperatures. It was the warmest on record. Of particular note was during the boreal summer, with over 20% of the land surface setting new temperature records, and everywhere in the planet, including all continents. And some of these temperature records were associated with extreme heat waves. For example, the one that occurs in Brazil, as well as the one I'm going to talk to you today about, which is the southwestern US heat waves, as well as other heat waves throughout the globe. Now, this specific event in the southwestern US was very special. It was the longest lasting heat wave in the region, where, for example, major cities like Phoenix, Arizona, experiences the longest stretch of maximum temperatures exceeding 40 degrees Celsius. That's 118 degrees Fahrenheit, which occurred from June 24 to August 17. Besides the high temperatures, the minimum temperatures were also at record high, with Phoenix also experiences the warmest minimum temperature in his history, with 36.1 degrees Celsius, which is about 97 degrees Fahrenheit for the low. Other places were also highly impacted by these heat waves, as far as New Orleans, for example, which set a record of 39 degrees Celsius on August 23rd. This heat wave was also notorious for the mortality associated with it. There were hundreds of deaths in Mexico, as well as in states like Arizona, Texas, Louisiana, and Florida. And for Arizona, Maricopa County, which is the county that hosts Phoenix, saw a 50% increase in the yearly deaths associated with extreme heat in 2023, as shown in this graph below. To show you how extreme this heat wave was, here I'm showing you on the right the temperature evolution for 2023 summer. And when I say summer here, I'm referring to the boreal summer from June 1st to mid-September. And that's what I'm showing you here on the right. You can see the maximum temperature in red and the minimum temperature in blue, with the climatological ranges and the 95 percentile ranges in shading areas. So these are the ranges typically used for defining what an extreme is. As you can see that after early July, both maximum and minimum temperature exceeded significantly the very high threshold of 95 percentile. And some of these exceeding temperatures were up to 4 degrees and 5 degrees above the 95 percentile, not just above the climatology. And this specific heat wave event that I'm interested in is this one here that lasted for 18 days. I already mentioned that records were broken when it comes to 55 days continuous heat, but not all days were associated with a heat wave. So I will talk to you a little bit more about what is a heat wave and the definition of that. But this specific event, as a heat wave characterized event, was 18 days long, and it was followed by 4 more heat waves during August and September of a smaller duration. To show you a little bit more of the spatio-temporal evolution of the heat waves, and here is a temperature anomaly map for daily maximum temperature, starting in June 15 and progressing every 5 days, all the way to 24 August. So that basically the entire summer, most of the summer. As you can see, the heat wave started early in the summer over Mexico, which was engulfed by very extreme temperatures and saw hundreds of casualties associated with that. The heat wave then started developing further northward. Then it subsides a little bit late June, and then it picked up again early July, moved north towards the US, and then eventually engulfing most of the western US by mid-July. This is during the peak of the event in the US. Then subsided back south into Mexico early August, and eventually moved northeastward towards the Great Plains, where many other records were broken, like, for example, the New Orleans record that I mentioned earlier. So as you can see, the summer was dominated by heat waves in at least for most of half of the US and Mexico. So we want to know what was driving these persistent heat waves. But also 2023 was a very special year when it comes to surface temperature records, not only over land, but as well as over the ocean. We saw that 2023 was a record for sea surface temperatures over most of the globe. For example, the Atlantic Ocean saw its warmest temperatures on record, up to 5 standard deviations above the climatological mean. And as you can see here on the right, this is just a seasonal cycle progression of temperatures average over the Atlantic box, North Atlantic box. And as you can see in red here, 2023 was warm throughout the year, but extremely warm, well outside the expected range. And 2024 followed, and it's also seen here in blue, where it's actually been warmer this year than last year. But our focus here is on 2023. Besides the record warm Atlantic temperatures, we also saw that the El Nino was in a growing phase during the summer months. So you had a growing El Nino in the Pacific, and most of the Pacific in the extratropics were also warm, as well as the Indian Ocean. So we hypothesize, this is a hypothesis, that there could be a physical connection between the longest lasting extreme heat wave that occurs over the western US and the record warm oceans, specifically the Atlantic and Pacific Ocean when it came to El Nino and the tropical Atlantic. But before we move on, I want to touch bases on why we care about heat waves. Heat waves are the #1 weather-related cause of death in the US. And as you can see here in this graph on the top right, the mortality associated with heat wave is increasing, and is disproportionately increasing more over the southwestern US, specifically over Arizona. So this is a very vulnerable region for heat extremes. Not only heat waves impact human health, but also the economy and the infrastructure. For example, the electric grid is highly impacted by significant heat waves, because it puts a lot of significant stress on power consumption, but also on power generation, because heat waves are often accompanied by extreme droughts. And some of the regions that depend on hydroelectric power generation are affected by low levels of water reservoir that are usually associated with similar weather patterns that heat waves are associated. As well as transportation is also impacted by heat waves. For example, there's a restriction that has to be put in place for takeoff for airplanes during extreme warm temperatures. Also, the agricultural sector is highly impacted through reduced crop yield because of extreme heat, as well as droughts. Besides that, heat waves are natural processes, but there has been many studies hinting that their occurrence is increasing, and is projected to further increase in the future. For example, a very famous study by Mill and Tebaldi showed that the ratio between extreme heat and extreme cold has been increasing, where right now you have more than, for every extreme cold event, you have more than twice the extreme heat events. But the impact of heat and extreme heat over, even at a national level, at a continental level, is inhomogeneous. There are regions where extreme heat is impacting more. So there's an asymmetric component of anthropogenic effect when it comes to heat waves. And that was shown in an earlier study done by our group. We show that this specific region over the southwestern US, anthropogenic climate change will play a big role in the occurrence of heat waves, where other regions in the US, natural variability may be more important. And that distinction, even at a country level, of how heat is driven by different factors is modulated by all the different spatial-temporal components and multi-processes and multi-scale interactions between different components of the climate system. For example, this study nicely summarizes most of the large-scale and to smaller-scale drivers of extreme heat. For example, on the longer trends, as I mentioned, anthropogenic effect has been shown to be a driving force when it comes to heat waves. But also natural variability at the multi-decadal timescale, like for example, Atlantic multi-decadal oscillation, which manifests as a sea surface temperature anomaly in the Atlantic Ocean and has a period of decades, has also been shown to be a dominant driver of heat wave occurrence over our country. In addition, on interannual timescales, we have seen that sea surface temperature variability in both basins, Atlantic and Pacific, is also a driver of heat wave occurrences and those timescales. On the shorter timescales of seasonal timescale, teleconnections from remote places, like for example, from convection over the East Asian monsoon can actually teleconnect and force an atmospheric waves that travels across the Pacific Ocean, which set up a large-scale pattern over the U.S. for promoting extreme heat. On subseasonal timescale, as well as synoptic timescale, we see higher frequency modes that drive heat wave, like for example, regional weather patterns, vegetation cover, soil moisture anomalies, as well as the well-known heat island effect are drivers of heat waves. And all these interactions may complicate the study of heat waves and trying to attribute a specific cause of a heat wave to a specific forcing mechanism. And we're trying to do that here in this study. So our studied region is the southwestern US and Mexico, and it has been shown by this study that there are many climate factors that are main drivers of heat wave occurrences in this specific location. Of course, when I say main drivers, I don't mean these are the sole drivers. These are just the most important component. There's interactions among each of these processes. But for this specific region, regional monsoons, as well as remote teleconnection and El Nino are mostly the dominant drivers, as well as tropical Atlantic sea surface temperature variability. So this is what exactly we're going to investigate today. And we're going to do that by looking at observational data, as well as reanalysis products and atmospheric model simulations. For observational data, we're going to rely on the Japanese 55-year reanalysis, GRA 55, for the period of 1955 to present. For daily and monthly mean precipitation, we're going to use the Global Precipitation Climatological Project. For sea surface temperature, we're going to use the Hadley Center SSTs, version 2 at a 1 degree resolution. And we also rely on observational data from stations over the southwestern US, taken from NCEI. Then at the later part of my presentation, I will talk about the modeling work we did. And for that, we rely on the state-of-the-art climate model, which is a community Earth system model. This is a CIMI-6 model. And for that, we're going to use an atmospheric general circulation experiment coupled with the land model and forced with observed SSTs. So how do we define heat waves? There's probably hundreds of different definitions, so there's no set rule of what a heat wave is. I like to define them based on not only a temperature threshold, but also a persistence, as well as a large-scale threshold. So heat waves are usually characterized as extreme temperatures, usually taking, and I'm taking that here as exceeding the 95 percentile temperature for that given day, that persists for a minimum of 3 days. And this will guarantee to filter out what is known as hot days or hot grid points. So we want to define them as large scale as possible. And this index that I'm using here is known as the excess heat factor, which is a combination of two indices. It's an acclimatization index, which look at the recent 3-day average temperatures minus the previous 30 days. And then the other index is exceedance over a high threshold, which uses the previous 3 days, and those average 3 days have to exceed the 95 percentile threshold for that given season. And the combination of the two gives you the excess heat factor. We also rely on cluster analysis for this work because, as I mentioned in the title and earlier, this heat wave was very uncharacteristic. It persisted for a long time. And we want to compare them, this specific event with previous ones, see whether it was different. And for that, we use a cluster analysis where we look at all the heat waves in the historical period that occurred over the continental US. And we clustered them. What we did was we used what is known as a agglomerative clustering algorithm, which basically merges like events into a single large event. And what we found is that there's 8 dominant patterns, special patterns of heat wave in the US, as shown here in the left. And one of them here on the bottom looks very similar to the heat wave that occurs in 2023. And I have to mention that when I did this cluster analysis, I did not include 2023. This is with data prior to 2023. So as you can see, one of the major heat wave clusters that affect our nation looks like that of 2023. So at least in a spatial sense, it was not an anomalous event. So we're going to compare 2023 with the previous event that looks like that. So here I'm showing you the distribution of temperatures, both minimum temperatures in blue and maximum temperatures in red from Phoenix Airport. And as you can see, and I already mentioned earlier, this 2023 event give you the warmest minimum temperatures on record of 36.1 degrees on July 19th. At the same time, it gives you the second warmest maximum temperatures of 48.3 degrees, 118 degrees Fahrenheit on July 19th. And I say second because July 18 also saw the same temperature. So in a sense, this is a very extreme heat wave when it came to amplitude. But now we compare on the right, we did a histogram of, I believe it's around 60 heat waves in the historical period that affected Phoenix. And we ranked them. We did just a histogram. We beamed all 60 events into a temperature anomaly above the 95 percentile. Keep in mind, this is 95 percentile. This is no climatology. The temperature anomaly with respect to climatology was much larger, up to 89 degrees Celsius. And this 2023 event was up there when it came to extreme amplitudes. So very warm temperatures. But what really is striking with this event compared to all the previous events is the duration. And within the duration of this event, as you can see, most of the heat wave lasts for 3, 4, 5 days, based on our definition. This extreme heat in 2023 lasted for 18 days, where the second place is 12 days. And that second place occurs this year in 2024. So in a sense, this heat wave was very extreme, very anomalous. Now we look into a little bit more of the dynamics of the heat wave and not only at the surface and see how extreme it was. For that, we rely on sounding data from a nearby station in Tucson, Arizona, where I couldn't find a sounding data for Phoenix at that specific time. But the heat wave was very large scale, so it affected most of Arizona and other places around it. So what we see that this is what is known as a thermodynamic diagram, or for meteorologists, an SQT log P diagram, where looks pressure is on the y-axis, it's logarithmic, and temperature is on the x-axis, but they are skewed at a 45-degree angle. And in red is just your temperature profile. In blue is your dew point profile, so how moist the air column is. And what we see that is at the very low levels, like not that low levels, from the surface all the way to around 650 hectopascal, we see that temperature follow what is known as a dry adiabatic. So you have adiabatic ascent. And at the same time, in blue, you see that from the surface to around the same level, the dew point follow this little dashed line, these are lines of constant mixing ratio. Think about it, constant humidity. So humidity was constant throughout the surface. all the way to 650. And what we found is that this deep layer has a very significant adiabatic ascent. Also, we found significant subsidence at mid-levels by this dew point depression here, somewhere around between 500 and 400 hectopascals, which is potentially indicative of subsidence, of sinking motion. And also, very notorious is the circulation. These are shown here on the right by the wind bars, very stagnant. These are very low wind speeds throughout the tropospheric column, which suggests the flow was very stagnant during the heat wave, and there was very little mixing with surrounding air masses. And I'm going to touch that next. So we look at a spatial distribution of the circulation motivated by this profile, and for that we rely on this map shows the potential vorticity at a constant potential temperature, and we use 350 Kelvin as the potential temperature or azeotropic surface. This resides somewhere in the upper troposphere. And what we found is that during this heat wave, there was a very strong anticyclonic circulation over the southwestern region. And not only that, we actually computed, besides the circulation, we computed something that's called a dilation rate. And a component of that dilation rate describes what sort of circulation is present. We use the dilation rate, which is given by this equation here, and we plotted where vorticity was dominating stretching and shear deformation, and that is an indicative of fluid trapping. So the air mass is contained in that region for prolonged periods of time. And when that happens, and if you have an anticyclone, you have a strong air mass modification of the source that will give you a heat wave. And I'm going to show you that a little later. So usually what we see during an anticyclonic circulation here, that is kind of like a block pattern with these thick vectors, which shows where the fluid is actually being trapped. Over these regions, you usually see increased surface short wave radiation, as well as reduced near surface relative humidity and reduced ventilation and a stagnant flow. This circulation pattern persisted for quite some time. So I'm showing you here that the same plot on the top left, but then this is the 7-day average, the 21-day average, and the 31-day average. And again, this anticyclone circulation was there for most of the time. Not only there, but also the fluid was trapped anticyclonically in this region. So again, increasing short wave rate heating at the surface, as well as reducing humidity, reducing ventilation, which all give you potentially persistent surface heating. We look at the column as well, not just at one isentropic level, which by reference I'm showing you here on the top right. And what we saw is that this is a cross-section from the equator all the way to 60 north, around 110 west, so more or less around the center of the heat wave, and a little, I would say a little east of Phoenix. And what we found is that significant surface warming and when it came to the potential temperatures. And you can also see a very deep anticyclonic circulation centered around 35. So this is the circulation. So into the page, out of the page, that's the anticyclone that's very deep in the troposphere. Another manifestation of the heat dome is a northward decrease in potential temperature. So what is known as a potential vorticity, which is known as potential vorticity inversion here, starting somewhere around 25 north. And we also see increasing in thickness of the azeotropic surfaces, which is indicative of mid-level heating and low-level heating. And then significant air mass trapping or stagnation, which is given here by the hatching and computed by the dilation rate that I mentioned earlier. And Phoenix lies somewhere here around 32 degrees. So this is right over most of the study area. So these are very significant anomalies. Now, the question is, why did those anomalies persisted for so long? Why we have 18 days of heat waves and 55 days of continued 40 degrees Celsius temperature over the region? For that, we rely on a heat budget analysis. We use the thermodynamic equation, which decomposes a heat tendency term into horizontal advection, vertical advection, adiabatic processes, and diabatic processes, which are comprising of short wave, long wave, diffusive heating, and latent heating. So we evaluate this equation at around 850 hectopascal, which is very close to the surface, but knowing the boundary layer, because that will include more complicated processes to explain. And we rely on daily anomalies. So these are for the anomalous circulation. And I'm going to show you that in the next slide. And pardon me, because this slide I know looks very busy, but I will walk you through it, what I did here. So this is just a time series from left to right. So on the bottom, you can see June 6 all the way to August 15. These are average every 10 days to make things more simple. And think about it as a multi-panel plot where there's actually only 4 panels. So the very top panel shows the geopotential high anomalies at 200 hectopascal, just as a measure of a heat dome. Then the second pattern shows the temperature anomalies at 850, where we evaluated all these terms on the bottom. The third pattern has many, many entries, 2, 4, 6, 7. Those are the heating rates as tendencies. And then the bottom panel, which has 4 entries, are the surface fluxes. And what we can see, and by the way, these are all anomalies. What we can see is that there is significant positive surface net short wave and long wave radiation and sensible heating early in the period, as seen here in the bottom plot, in the bottom panel, as well as enhanced heating rates in the mid panel, mostly due to vertical advection, so subsidence. Then what we saw is that there was a rapid increase in 850 hectopascal temperatures here, as you can see in the early periods, as well as a rapid increase in the atmospheric thickness as measured by the geopotential high anomalies. This is in June. Now in July, most of the anomalies were related to surface heat fluxes and diffusive heating, which kept the temperature anomalies very warm throughout July, as you can see here in the second panel. And in August, the temperature anomaly started subsiding a little, but then surface sensible heat flux as well as long wave heating kept it a little bit going and was supporting further the progression of the temperature anomalies late into August. And I want to mention that circulation anomalies, when it came to horizontal advection, played very little role. This is very common during heat waves because usually these terms, the circulation terms, cancel each other. Now, the surface latent heat flux was, for most of the summer, was extremely negative, meaning there was little moisture there, which led to an exacerbation of the surface sensible heating as well as the increase in the surface temperature. I'm going to touch on that now, what drove this extreme reduction in the surface latent heat flux. This plot here shows for the month of June, the larger scale anomalies, sea surface temperature anomalies, which, as I mentioned earlier, you have a growing El Nino in the Pacific and extreme warm Atlantic Ocean. Now, the sea level anomalies, as you can see here, the means, the climatological means are shown for reference as a black contour, whereas the anomalies are the color. You can see that there was a strong reduction in what is known as the Bermuda high, which is the subtropical high over the Atlantic, and the Pacific counterpart was enhanced. So the subtropical high over the Pacific was enhanced. And precipitation show your classical El Nino pattern with southward shift of the ITCC, even though this is still early summer, El Nino was already developing. And the opposite pattern was shown in the Atlantic. So you have northward shift of the intertropical convergence zone. Now, what occurs over the Gulf of Mexico is very intriguing, which shows very dry Gulf of Mexico and wet east of Florida, which I mean is indicative of potential retraction and weakening of the subtropical high. Similarly, in July, now El Nino is still growing, and then now the Atlantic sea surface temperatures are more homogenized, so it's warm pretty much everywhere. The subtropical high over the Atlantic remain weaker than normal, and the Pacific went back to sort of a climatology. And you can also see reduced mean sea level pressure over the heat wave region. This is expected because the heat waves will give you what is known as a heat lobe at the surface. Interestingly, over the same region, you have reduction of precipitation, as well as your typical southward shift of the ITCC during a growing El Nino. So we ask the question, is the reduction in precipitation and the reduction in latent heat flux that I showed you earlier during the heat project analysis responsible for the heat wave, and what drove this reduction? This region is very notorious for a specific region. This region is strongly coupled, where temperature, surface temperature, and soil moisture are strongly coupled. And most of the rain over these regions occurs in the boreal summer and are associated with the what is known as the North American monsoon, which provides moisture and rainfall over the region. And as you can see here, this is a satellite view of the North American monsoon for a specific day. This is your weather pattern, but you can actually see the circulation coming in from the Gulf of California into Arizona and New Mexico. So it is important to assess the state of the North American monsoon in 2023, and if we can explain the reduction in the latent heat flux and precipitation in the region because of the North American monsoon. And we did that we computed a monsoon index. And then what we found is that the North American monsoon was one of the weakest in the observational record in 2023, as you can see here in the top graph. Now, the North American monsoon has two moisture sources, one from the Pacific, usually at lower levels, up to the Gulf of California from the Pacific. And then another moisture source comes from the Atlantic through the Gulf of Mexico at a little higher elevation. Both of these moisture sources were basically reversed in 2023, where you have more like a northwesterly moisture flux anomaly, which led to moisture flux divergence over this region, which is shown here in color. And most of the moisture went into the Gulf of Mexico and south into the intertropical convergence zone in the Pacific. So our question is, we have a growing El Nino, we have an Atlantic warm, and then we have a reduction in the monsoon and retraction of the subtropical high in the Atlantic and expansion in the Pacific. Did those components play any role in the occurrences of the heat wave? This question is very hard to answer and pinpoint specifically what drove that. But what we did was we used a model experiment. This is a climate model experiment using CESM2 as the model. And what we did was we had two experiments. One where we prescribed just climatological sea surface temperatures, and we ran it for 100. We ran it for 100 ensembles. Then we did the same thing and have a second experiment of what I call here E23, where we prescribed 2023 SST evolution globally. We ran this model at 1 degree resolution with constant CO2 forcing. And this is the SST evolution that we prescribe to the model. As I mentioned, we have 100 ensembles, and we characterize any role that sea surface temperature played in what we may see in the model, as just taking the difference between the ensemble mean of the prescribed 2023 runs minus the climatological runs. We use the ensemble spread, the difference between each experiment, as an estimate of weather noise. So we call it uncertainty. And since we're dealing with heat waves, and I use T95 as a threshold for defining what a heat wave is, it's good to evaluate whether CESN is able to reproduce the observed extreme threshold. And that's what is shown here on the right. It's not perfect, but at least the spatial patterns are fairly accurate, I would say. So this is our results from the model experiment, and everything I'm showing you here is just taking 2023 prescribed sea surface temperature runs minus climatology runs. So you can think of it as SST-induced circulation changes. So what we see is that upper level heat dome anomaly, as measured by 200 hectopascal temperatures from the model, mostly over the heat wave region, which coincided with an anticyclone at the same 350 Kelvin isentropy level. This is vorticity, and I want you to know that the color bar are reversed. So I just shaded red for negative, meaning anticyclonic, just because we're talking about heat wave. Just to have some relevance here. But again, you see a blocking pattern, an anticyclone in this experiment that is consistent with what we see during 2023. Now we look at the surface, and again, 2023 minus control simulation, and what you see here is enhanced short wave radiation over over our analysis region, as well as enhanced long wave radiation, which tells you clear sky. And also at the same time, at the surface, we see enhanced surface sensible heat flux. So basically increased surface temperatures at the expense of reduction in the latent heat flux. So this reduction, less precipitation in this region. So less soil moisture to compensate the enhanced heating. So in a sense, this is well correspondent with what we observed in 2023. We computed the heat waves in the model. So we follow the same thing. We follow the excess heat factor definition that we use in observation and computed the heat wave for the two model runs. And we decompose those heat waves into its components. So what we see that, again, the experiment of 2023 prescribed minus climatology. And here I'm normalizing by climatology just to give you a perspective on percentage change. And what we see is that the amplitude of the heat wave increases mostly over Mexico, but the number of events is increased for most of the region, as well as the duration, the number of days under heat wave is also increased by even 200%. And the duration of the event is further increased by about 40%. So this is consistent with what we see in 2023 with the long persistent heat waves. This is a table just looking at the two model runs, control simulation versus climatology, control simulation, which is climatology, versus 2023 for different heat wave characteristics. So we look at mean maximum temperature change. It's about a 1 degree warming, a warmer summer. We look at the return period of a very high threshold, like a 45 degrees Celsius temperature. It occurs every 45 years in the control simulations, climatology, and the return period drops to about 14 years. So it becomes more common, more recurrent when we prescribe 2023 SSTs. Same thing with minimum temperatures. The return period drops for a very high minimum temperature of 31 degrees Celsius. But then we look at the heat wave characteristics. We saw 77 events in the climatological run, whereas we saw 184 events in the prescribed 2023 SST runs. And the heat wave days almost triples. The duration of the heat wave increases from almost 4 days to 4.6 days, but the longest heat wave in the control run is just 9 days, whereas in the 2023 SST prescribed run is 14 days. Also, the amplitude is a little stronger as well. So here is a schematic diagram summarizing everything I have said thus far, is that the Atlantic Ocean was homogeneously warm, not just warm, record warm. At the same time, in the Pacific, you have a growing El Nino. So you have warming over the tropical Pacific. We also saw that in the Pacific, the subtropical high was enhanced. And in the Atlantic, the subtropical high was reduced. This led to a reversal or a weakening of the North American monsoon, where you typically have moisture flux from the tropical Pacific into the monsoon, as well as moisture flux from the Atlantic and Gulf of Mexico into the monsoon. This circulation was significantly weakened. And you have moisture flux divergence here, so depletion of moisture for the monsoon, which you end up with one of the weakest monsoons in the historical period. All that led to a heat dome over this region, which persisted for quite some time because all these climate features were fairly permanent throughout the summer. So you end up with half of the summer with extreme temperatures over the region and a heat wave. Now, I mentioned 2023 was special, but 2024 is probably more special. As you can see here, I mentioned that 2024, this is the evolution of the surface temperature over the Atlantic. And you can see that 2024 has beat 2023 when it comes to heat. And in the Pacific, the story is a little different. Now you have during the summer, you have a fairly neutral condition, and El Niño is being expected. So coincidentally, the Southwest US was no stranger for heat waves this year as well. And that 55 days continuous 40 degrees temperature over Phoenix was broken this year, 56 days. And I believe it's even more now. So other places also saw, including Phoenix, saw the earliest ever 43.3 degrees Celsius, which is around 110 degrees Fahrenheit temperatures, very early in the summer. So we had the question, did the warm 2024 SST in the Atlantic contribute to the 2024 heat wave, what we're seeing this year, just like as I showed you earlier for the 2023 case. And I'll leave you with my conclusions here, which I already summarized in the schematic plot, and I'll take questions. And thank you for your attention.